for sure.
Yeah, maybe just one final point, Emmanuel. I always like to tell people, we're the ALD experts. We're not the device experts, right? So
Yeah, yeah,
what
yeah,
we work best in that collaboration. When somebody is saying, "Here's my pain point. This is the hill I can't climb, or the barrier I can't get over."
yeah.
What can you guys offer? What have you seen, and what ideas can you come up with? So that's really where we found that kind of relationship and those collaborations to be the most successful is when somebody else says, "Hey, we have this giant nail. Do you have a hammer for us to hit it with?" Right?
Yeah, absolutely. Absolutely. That's what I love about, I've been here in this particular role at Power America for just a few months, but it's one of the things I love about this community is the fact that we inherently require collaboration in order
Hmm.
to be successful. We have to work together in order to make all of this happen. So I'm
Yeah.
really excited about your presentation today. I'm excited about the potential for, what it means for the future of wide bandgap and ultra wide bandgap devices. So um,
Yeah.
yeah.
Great. Thank
All
you.
right,
Yeah.
we're at the top of the hour, so I'm going to go ahead and we'll get us started. Thanks so much for folks that have been able to join so far. We know you may still be connecting. I want to give you a moment just to make sure you're able to see the information being shared and to hear us as well. We are very excited about today's technical webinar. As you all know, we do this on a monthly basis. This is an opportunity to hear about some of the cutting edge developments that are happening in our field and to hear from folks within our community. So we're glad to have you all with us today. We're joined today, and I'm sorry, I didn't ask the proper pronunciation of your last name, Dr. Matt. I'm gonna go Weimer.
You got it.
All right, awesome. I before E, it's you never quite know in English. So
Absolutely.
but we appreciate having you with us, joining us from Forge Nano. Dr. Weimer holds a PhD in chemistry from the Illinois Institute of Technology and is a surface chemist that specializes in atomic layer deposition, or ALD. For the past 5 years, he's led the wafer development team at Forge Nano, overseeing applications development, customer demonstrations, and the company's wafer scale ALD laboratories. He's also played a central role in launching Tefra, which is Forge Nano's ALD cluster platform, which is uniquely designed for more than more market, focusing on logic and memory and compute devices. Previously, Dr. Weimer held a postdoctoral appointment at Argonne National Laboratory in fundamental battery research and then joined Lam Research in new products development, contributing to next generation process technologies. So 5 years at Forge Nano, about 15 years or so in ALD, lots of expertise and experience in getting technologies out into the market and into commercial use. So really excited to hear from you today. We're going to turn things over to you, Dr. Weimer, and then we'll be back later for the Q&A. I will also just prompt everyone, if you have a question, please make sure that you jot it down, write it down, drop it in the chat. I'm not sure if the Q&A module, I believe the Q&A module, yes, Q&A module is active. So if you have a question at any point in time, you can type it into the Q&A module, and then at the end during the Q&A session, we'll go through and we'll address them all. But don't feel that you need to wait to give us your questions. All right, Dr. Weimer, over to you. We appreciate having you today.
Wonderful. Thank you, Manuel. That was a very kind introduction. I'm happy to be here. It's really great to be doing these technical webinars. I think they provide a really great way for people to learn about things they might not otherwise encounter. So yeah, as Manuel mentioned, I'm Matt Weimer. I've been at Forge Nano for about 5 years. We are an ALD company, atomic layer deposition. So that's really where our expertise lies. So I'm, kind of, we'll say, moonlighting a little bit in the power electronics field. It's not my field of specialty, but I've been here for a couple of years and really enjoyed the learning that I've gone through, learning about devices, how they work, and how they're made. And so today, I really want to focus on how ALD has enabled the sort of current market of GaN and silicon carbide, but also kind of do a little bit of a look ahead for the ultra wide bandgap materials, and again how ALD can influence and impact those. And so, I don't want to assume anything here. I want to make sure we all know who Forge Nano is. As it was mentioned, we are an ALD company an American-made, American manufacturing company just outside of Denver, Colorado. We also have we're building out a battery factory in Morrisville, North Carolina, not too far from where you all are down there at NC State. But that's a whole other side of Forge that I don't get to talk to today. Yeah, so exactly. So again, the real focus for the wafer side of Forge Nano is equipment sales. And so, again, as mentioned, we have a couple of tool offerings that I'll talk about later. Really that the goal there is to sell equipment that's reliable with, best in class service. So, we're about 120 people now. We have a nice clean room up here that we just built out that has space for, both building tools, but also running device wafers. We can do all the particle measurements and all that kind of fun stuff. It's sort of my new playground. I really enjoy it. We are still investor funded, VC funded, but there was I can say this publicly. There was a recent announcement that Forge Nano is going public. We plan to be listed on the Nasdaq by year's end, so that's another big step for the company. We're really excited about that as well. Okay, so let's move on to why we're here. I'm sure this slide is a lot more familiar to most of the audience than it is to me. So at the risk of perhaps butchering it, we have this nice power versus frequency graph on the left that has sort of the shaded area where each type of device outperforms the competition. And so, it seems like a lot of what people have been using is really silicon based, whether it's a MOSFET or an IGBT. However, once you go to a high enough power, silicon carbide MOSFETs are just superior from a size and an efficiency standpoint. Really, heat is also key. Of course, when you go to a higher frequency, the GaN HEMTs take over, right? They outperform silicon and they outperform silicon carbide. But perhaps more interestingly is this area where they kind of overlap. Which one is the right solution for this sort of middle power, middle frequency range? Is a very interesting space, I think, to explore for this community. And so, there's different applications that sort of live in all these different areas. And the one that I want to talk about, which is, I think, the most topical, is how these silicon and silicon carbide and GaN devices can help the efficiency of data centers. So on top here, this is a general schematic that I borrowed from Navitas about how energy is moved in a data center. And without going too far into the details, there's transformers. We go AC to DC and then DC to DC. Server rack is about 100 kilowatt. However, people have been trying to push GaN and silicon carbide devices to improve the efficiency and reduce the size of the certain steps in the process. And so some of these I have listed here below, the different power and the devices. Silicon carbide's in orange and GaN is in blue, where it either has been or will be potentially used to increase that server rack power, obviously reduce the size and increase efficiency. Now, again, this is not my area, but I've read that with efficiency numbers here, you're usually in the high 70s, maybe high 80s. But with some of these or most of these changes, your efficiency in energy efficiency in this path can get above 90%. And of course, that doesn't mean we use sort of 10% less power. What it really means is we get 10% more compute, right? Nobody's going to dial back their consumption. They're just going to be able to use more of it. So, I and Forge Nano believe that silicon carbide and GaN powered devices really are the next step in enabling hyperscale computing. All right, so now that's what we're here to, what people I think are most familiar with. I'm also very interested in ultra-wide bandgap materials. So here's this nice graph on the left where we look at specific on resistance versus breakdown voltage. And we compare these compound semi materials and also diamond versus silicon. And so it's pretty clear that some of these other materials have this higher breakdown with a lower on resistance. They have, so that's a huge advantage, which means you can also reduce size. Some of these are also better in harsh environment. So when you think about, DOW type applications or space applications, there's a clear path where these can outperform GaN and silicon carbide. However, there are some challenges, right? So just because the theoretical breakdown at a specific on resistance is written on this line, it doesn't mean we can actually build a device that is capable of achieving that. And I think this is, from my perspective, where ALD can really help things. ALD is great at controlling the interface quality, so that includes interface defect density. Excuse me. So as we sort of talk about this and coming up, I will try and talk about it through that lens because I am not a bulk material expert. So and of course the last thing we always want to be cognizant a little bit of the availability of material. Diamond is probably the one that I think is probably the flashiest. Who doesn't want a diamond device? It just sounds cool. But getting a substrate that's large enough to be cost effective, not to mention being able to etch features into that diamond, can be quite a challenge. Okay, and so before we get into it, I just wanted to put up here and speak to very briefly how ALD has already impacted silicon carbide and GaN. And if we start going from left to right here, the first thing that it seems people always think about with ALD is an environmental protection. Another way to say this is a hermetic barrier. And so I kind of call this the gateway to ALD because you see what it's capable of, you get comfortable with it, and then you realize you can use it in a lot of other places. And so here I'm just showing a nice GaN structure, GaN hem structure, just as an example of what what we've coated with a moisture barrier to protect it from the environment. And so from our perspective and from what we've seen in the market, this is really applicable to both silicon carbide and GaN, and it's kind of architecture agnostic. We'll talk about the fundamentals of ALD in just a minute, but remember, ALD is a conformal technique. That means anywhere the gas can go, you'll get the same quality and same thickness of film. So, with these little divots here, whatever features that you have on your device, it will get the same amount of ALD, even down in these deep, dark corners. All right, so the next one in the middle here is a dielectric barrier. This one has really been popularized by the silicon logic space. I have a slide later that shows the history of ALD in the semiconductor industry, and so this was sort of the first big breakthrough for ALD and silicon microelectronics, being the gate dielectric. And so it's been adopted in a couple of places for silicon carbide and GaN, but from our perspective, the most the place where people have to come to ALD is in trench architectures, right? When you get features that PVD or excuse me, CVD can't coat uniformly with a high enough quality film, and thermal oxide for, let's say, silicon carbide doesn't work, it's really ALD or nothing. Okay. And then finally, we have sort of a unique application for gallium nitride, and I have a slide on some of the details later. So just briefly, with the architectures that we've seen, there seems to be some interface defect density that ALD can really help with. There's been some really good reviews and a lot of good research about what the identity of those defects are, and it seems like ALD has some good alignment with removing some of those. And so this, from our understanding, is already used in production. There was a lot of work at IMEC to kind of develop this and push it forward. Okay, so as an overview for the rest of the webinar, I want to make sure that we all understand what ALD is. I think a lot of times when I speak with people in these industries, they have a basic understanding of ALD, but there's maybe some key pieces missing, and I want to try and fill in those gaps as much as possible. I also want to explain why the tools that we have at Forge Nano are unique, and why we believe we can do better and different things. And then I'll dive in a little bit to some of those wide bandgap silicon carbide GaN applications, specifically some of the work that we've done as well, and then look at some ultra wide bandgap stuff, specifically gallium oxide and diamond. Okay, so here is ALD in a nutshell, a very small nutshell. If we start on the left, this is a schematic that we in the ALD industry love to use because it simplifies ALD down to Lego blocks. As a chemist, this is hard for me to see because, I believe these are all chemical reactions, and I think it's important to understand those. But let's keep it simple for now. So just kind of walking from left to right, we have a surface that has some reactive site. That's this blue divot. We then introduce a precursor. That precursor has a complementary reactive site. That's this blue spike, light blue spike. Those spikes meet the divots and you fill the whole surface up. You get one single monolayer, and then the reactions cease. The spikes don't react with the spikes. So you can put as much of these blue spiky precursors in as you want, and you will not get any further reaction, no more than this monolayer. Of course, now you have to remove all of these blue spikes. We call that the purge step. This is actually why ALD is so slow. You have to remove all of the precursor because you need two precursors. They have to be separated both in time and in space. They should never see each other. Okay, so there's also not shown here is a reaction byproduct. Sometimes that can really affect things, but not all the time. But let's keep it simple for now. So look, we've done one half cycle, not even a full cycle. Let's move into the complementary precursor. We call it the B precursor. It's these blue bow ties. Those blue divots, dark blue divots, meet up with those spikes, and we do the same thing. We get a nice monolayer of coverage. And of course, now we have to purge again. That slow step. We've now completed one cycle of ALD. It's pretty neat because we get a digital amount of film with each cycle. That's typically on the range of sub-angstrom scale. So maybe you get an angstrom. There are a couple processes that are a little more, but you get very fine thickness control that you can then build up into the film thickness that you desire. So there's a lot of cool things that come out of this. I'll talk about that on the next slide, but I wanted to show a little bit of history of ALD in the silicon microelectronics field and really point out what happened in 2007. As I sort of alluded to earlier, this is when ALD really had its moment in the sun. Intel was struggling to reduce the node size from 65 to 45 with their existing dielectric technologies. So they adopted ALD of hafnium dioxide as their high K metal gate dielectric. It gave a high quality film, and at this point in history, Intel was like the standard for manufacturing in the world. So for Intel to say ALD is a high volume manufacturing technology, everybody else agreed. So that was really when ALD became a known commodity, as it were. Since then, it's also enabled a lot of things. One of my personal favorite is for 3D NAND. It really enabled the stacking of 2-dimension to 3D for NAND flash. Okay, I won't do too much more history, but we'll move on to some of the chemistry. Like I said, I am a surface chemist. I know most people shudder when they see chemical reactions, but I do think it's important to just casually understand what's actually going on the surface. So if we just briefly walk through this, we've replaced our blue spikes with these molecules here. We'll even call this something specific. This is trimethyl aluminum. So these are 3 methyl groups, CH3, and this is an aluminum atom. The surface, those blue little divots, is now our hydroxyl. So when this molecule sees the surface, we move a proton and generate methane. But more importantly, we now have a new oxygen aluminum surface bond. That's critical because in this process, by definition of ALD, we have really good surface adhesion, right? So that the film adhesion strength is as strong as those bond strengths, which is a really important thing when you think about the quality of ALD. So the one last thing I'll point out here on this slide is once you get that full monolayer of TMA on the surface, now the surface looks like a bunch of methyl groups, which looks a lot like TMA. So once this surface looks like itself, that reaction stops. This is where the self-limiting nature of ALD really comes out. And so just for completeness, the second half cycle here is water, but we do the same chemical reaction where we're moving a proton and generating methane. Just as a brief aside, methane as a reaction byproduct, it's pretty benign, right? It's actually kind of hard to do stuff with methane, but there are a lot of other ALD reactions that produce byproducts that aren't as benign as methane. But that's maybe a topic for another time. All right, so this is kind of a fun slide to talk through because it shows some of the benefits in pictures. Again, I think that the thing that most people understand and think about ALD is that conformal coating that I've mentioned a couple of times. And on the left, we have this V-shaped via in silicon where the ALD film is filling it up without a gap or without getting pinch off or anything. I've already talked about precise precise thickness control. But one of the things that comes out of that are what are called multi-layers. We also call them nanolaminates. And that's shown on the left here, where two dissimilar materials are actually separated in layers. It's a really interesting way to tune bulk film properties. Some examples that I'll talk about later are, as an environmental barrier, doing this laminate scheme reduces the permeation of water and oxygen by orders of magnitude. You can also tune dielectric properties. You can think about reducing leakage current by putting in a low leakage material in a sort of higher leaking material. So there's a lot of games that we can play and a lot of interesting stuff. Talked about surface adhesion already, but I think this is sort of a good place to talk about this middle image. We do a lot of powder and particle ALD here at Forge Nano. So we have this cool image of a roughly 50 nanometer particle with about 5 nanometers of ALD. And it's pretty apparent from the image that there's no cracks, there's no pinholes. You get a nice uniform 5 nanometers all around it with good adhesion. So from a film quality perspective, I just really love this image. It really highlights it. And for those of you that aren't familiar, typically ALD happens below 300 C. There are a few processes for nitrides that drift up higher, but typically ALD is considered a low temperature technique. All right. I've just spent, maybe 10, 15 minutes telling you why ALD is so great. But let's discuss why it's challenging. And it really comes down to speed. And so, I wanted to start by kind of showing what reactors look like to kind of help you understand why this is a problem. So the typical type of ALD reactor is called a cross-flow or a laminar flow type reactor. All three of these are. So you can just, flow chemical directly horizontally across the wafer, whether it's a shower head, which is what our tool looks like, or batch. All of the processes are considered laminar flow. Here's a plasma enhanced tool cross section for those of you that are interested. We're not going to discuss that too much today, but I did it quite a bit in my career, so happy to discuss if anybody has questions. So in all of these orientations, you have to choose a pressure regime to work in. So if you choose a high pressure regime, your precursor molecules are moving more slowly, which means they have time to sort of travel around the reactor, diffuse out of their laminar flow lines to give you a uniform film thickness across the wafer. But because those molecules are moving slower, it takes longer to purge. As I mentioned before, that's the big slow step in ALD. There's also this horrible relationship where the more precursor you put in, the longer it takes to purge, and therefore the slower your ALD process is. So a lot of people said, all right, let's go to low pressure. This is how 300 millimeter silicon tools work. And it works. You do have shorter purge times, but you find out that you have to put a lot more precursor in to get that uniform film that's required. So the amount of purge time that you are reducing is not as much as you would actually calculate. So, you still aren't really breaking that trade-off. And so that's, a good segue into why what we do is unique. Here's a nice, we'll say, generated image of our recent high volume manufacturing tool we call Tefra. It's built on the technology that has three key differentiators. The first is the hardware. We call these fast pneumatic valves. This is how we introduce the precursor. Those work in tandem with the reactor design, which we call synchronously modulated flow and draw. It's a mouthful. You can call it SMFD if you like. And then we prefer to use surface chemistry over plasma to improve our film properties. I won't go into this too much, but I will touch on this a little bit. Okay, so very briefly, our ALD tools have these fast pneumatic valves that they're proprietary. We make them in-house. They look much different than your typical ALD swage lock valve. For example, there's no VCR stub. So these are really optimized to minimize dead volume. Again, the less precursor you put in the chamber, the faster your ALD is going to go. And so we do what's called a face seal with these, where we stack them on top of each other to introduce precursor while minimizing that dead space. But really, the thing that sets these things apart is the actuation speed. We can do a full open close cycle in 3 milliseconds. We've tested this quite often in our lab. It's quite fun because you get a really fine control over the number of molecules that you're putting in the chamber. It's pretty cool. And they're primarily stainless steel, so they're good up to 200 C. We've been running these for years, so we know they're stable. So these really work in tandem with the reactor design. Again, that SMFD, we're a single wafer ALD chamber, so not batch, single wafer, have that shower head design, but we encapsulate our deposition zone with a nitrogen gas curtain. We call it a draw control. And essentially what that draw control does, it allows us to access the high pressure regime and the low pressure regime each when we want them, right? So that trade-off I was talking about before, we get the benefits of each regime while ignoring or avoiding the detriment. And so, we have this little cloud here that shows we're holding the precursor when it's on, and then when we turn it off, the precursor flies out of the chamber. We're always pumping on the chamber with a turbo pump, so we know we get down to base pressure quite quickly. And so, a couple of key things to think about here is we get really high precursor utilization. I think for our TMA water process, we are typically above 80%, sometimes above 90%. And for the exposure time, we're usually in the 4 to 5 millisecond range. For more challenging processes like nitrides and metals, sometimes we're up in the 50 millisecond exposure times. But because we're able to sort of circulate the precursor here, we just use much less of it. And because we have the sequence of on and off with the draw control, especially for oxides, our typical purge time for each half cycle is around a half a second. So when you put all that together, we can get deposition rates for ALD that are above 10, sometimes 12 nanometers a minute. Now to kind of level set that, there are some ALD processes that can get close, but typical ALD processes for like silica or hafnia, they live in the sub-nanometer per minute range. So it is quite unique. All right, and finally, the surface chemistry that we like to take advantage of, we prefer to use surface catalysis over plasma. Again, as a chemist, from my perspective, when you introduce plasma or higher temperature, all you're doing is beating that poor reaction with a larger energetic hammer. If you want a reaction to go forward, there's other techniques that we have, been studying for hundreds of years, such as catalysis. So using small non-metal catalysts to push reactions forward, really, you're lowering that energetic barrier to help them along, is a much more elegant way to do things. This is a field of study in the ALD community that's just starting, but I think there's a lot of potential and a lot of low-hanging fruit. And so, without going into the details of how it works, there's some sort of net benefits of it. First is you get a much wider temperature range where your ALD will occur, especially going to lower temperatures. You also use your metal precursor more efficiently. And finally, typically you have less impurities in your film and higher quality. Say we're measuring with like density or even dielectric properties. And so, silica, we call this CRISP. Our silica CRISP process is sort of the flagship in this, and I'll talk about some of the properties in just a bit. Okay, so as a sort of a brief overview and maybe a sort of transition slide, with our draw control, that SMFD, we can achieve full wafer uniformity with much less precursor. It's sort of a little bit easier for us because we're mixing the precursors in a different way. We're not just relying on laminar flow lines and diffusion. Nanolaminate encapsulation, that's always the headline application. And we can do that quite regularly, quite easily in our tool. Typically, the tools are outfitted with 3 metal precursors, so you could even make a ternary oxide if you felt so inclined. Also, people always ask us, well, this faster ALD, is it still ALD? Do you still get a conformal film? So this is my favorite example of how it is conformal. This is our tinitride film doing gap fill on silicon dioxide features. These are, only about 2.5 to 1. But the fact that we're able to fill these features without a gap shows that our process is still ALD. So the cycle time on this one was, right around 1.5 seconds. So quite fast. And then, finally, the other question we get a lot is with the surface catalysis, with the CRISP process, is that still ALD? Is it still conformal? So this is a silica CRISP film coating in black here. These are horizontal features that are about 35, 36 to 1. And the ALD film coats this conformally. It's harder to see here, but it's actually performing gap fill as well. We know that these features were coated because they were stress tested and passed with flying colors. Okay, and the marketing people would kill me if I didn't put this slide up. This shows our tool offerings. In the R&D world, I get to play with both the R&D tool, which we call Thea, as well as the high volume manufacturing tool. I have both of these in my lab. They're basically the same. They both have that same set of valves, the same reactor design, but the Thea, it's built to be a little more flexible. It's sort of custom made for R&D. You can have more precursors that are harder to deliver, and you have a different sort of chamber volume and dimensions. So it's maybe a little bit slower than the high volume manufacturing tool, which is typically designed for, like I said, 1 to 3 processes. The Tephra platform is pretty great. We have 4, 6, and 8-sided platforms. We have oxide modules, nitride modules, elemental modules. So you can kind of mix and match depending on the needs of your fab or your foundry. We do have one more version that I haven't shown here, where we have one of these Tephra modules on just a standalone cassette load port. So you don't actually have to have a transfer chamber, but that's a very, maybe we'll say, low volume type application. Okay, great. So that's a rundown of the tools, about halfway through. So I think this is probably a good time to transition to some of those wide bandgap applications, show some of the work that we've done. So as I mentioned at the outset, a hermetic barrier is where ALD is the first thing people think about when they think about ALD. And so, I've sort of put this GaN-HEMT schematic here for consistency. We call our platform the ALD to the X platform, and we have a product that we call the ALD cap. Typically, it's a nanolaminate. So remember, that's the 2 individual layers, sort of repeated, of aluminum oxide and silicon oxide, though, we can sort of mix and match depending on the application and the need. So, I put some oxygen and permeability and water vapor transport rates just as examples. But one of the things I will mention, and it's a question I get a lot when we talk to people, is, well, why can't we just do a single layer of aluminum oxide? Typically, when you compare a film, let's say 50 nanometers, the same thickness of aluminum oxide versus a nanolaminate that, let's say, it's a ratio of 9 to 1, the permeability of oxygen and the water vapor transport rate decrease by an order of magnitude or 2. So depends on the application is the real answer. Sometimes a single bulk layer of alumina, that's enough. But for a lot of, say, telecom applications or even data center applications, you just need better protection. So that's the first point on this slide. The second thing I love to talk about is this comparison between PECVD. So we had a customer that had an existing silicon nitride PECVD moisture barrier of 800 nanometers. They couldn't get it to pass their accelerated testing requirements. In this case, it was they actually needed to get to 384 hours at 135 C and 85% relative humidity. So we said, hey, let's see what the thickness we can get done with the ALD cap solution. So at 10 nanometers, we were actually able to pass 96 hours at HAST. So if we kind of pause there for a second and think about the implications of that, we have 80 times less film and it performs better. So yeah, ALD is slower, but if you only need, 1/80th or heck, even 1/50th the film, you're not really losing that much time. And so, we put the deposition time here as a column to kind of highlight that we're actually faster and have better performance. So, again, to pass their spec, they wanted 384 hours. So that, we did that with 20 nanometers, takes about 2 minutes. The eventual application for this customer was 50 nanometers, but they wanted a wide, we'll just say they wanted some extra security. So, again, I think what I want to stress for people is, PECVD is great because you know it, but it might not be great for what you're using it for. All right, so let's move to that middle column from before, dielectric barriers. So let's focus on silicon carbide. I think there's a lot of discussion over, sort of what the next generation of dielectric barrier needs to look like. And so we feel like our silicon dioxide crisp film is a viable solution. And so here's some work that we've done with Purdue University and then the University of Arkansas. So the first thing I want to talk about on the left here is leakage and breakdown. And so I'm comparing the as deposited crisp film with the same film after a nitric oxide anneal at 1150. And so the first thing that I think jumps out is that the leakage, it does decrease a little bit, but it's already pretty low, right? At 3 megavolt per centimeter, that's a pretty good leakage. The second thing is that the breakdown occurs at roughly the same spot, right? So which is above 10 megavolt per centimeter. So this tells us a couple of things. First of all, that our silica crisp film is very high quality. Second, it tells us that the nitric oxide anneal isn't really impacting these. So what does it impact? Well, we know that it does impact the hysteresis that we observe when we sweep in a CV sense. And so here on the right, as a transition, I should briefly mention, this is what the structures that we're measuring in both cases look like, roughly speaking. We have some ohmic contact, the silicon carbide, and then 30 to 50 nanometers of the silicon dioxide ALD. And then we have different pad diameters. This is a top view of that contact. And so, maybe jumping back into the CV sweeps here, now we're comparing just a thermal oxide versus ALD silica crisp versus a PECVD. And so, one of the things that really stands out is how vertical that sweep is for the ALD film. It certainly looks better than all three. And then, not shown here, but when we looked at the hysteresis of these films, the ALD film performed the best of the three. So, again, this isn't too surprising. People sort of already know that ALD gives a higher quality dielectric than thermal oxide, obviously, or than PECVD. But it's always important to prove it out on the specific device. I'll talk about this a little bit later with hafnium dioxide, but you will see different film properties, dielectric film properties, depending on the substrate. So that means that interface between the ALD film and whatever you're putting it on really matters a lot. Okay, so as one last point here, again, as some people transition to trench features, ALD is sort of the best solution here, and really the only viable game in town, again, from our perspective. Of course, we can maybe have a broader discussion about whether the transition to trench will happen or if people just want to stay planar. But I think it's our perspective that some part of the market will transition to trench, and that it will require a high quality ALD silicon oxide dielectric. Okay, so I promised some film properties for the silica crisp. I always like to compare it to a PEALD film, a plasma enhanced ALD film, because that's really what you see for silica in the market. Most thermal silica films are quite low quality. So this was pulled from a couple of different papers using a very similar precursor at a similar temperature. And there's, a couple of productivity takeaways. We have shorter deposition time. Again, this was in the literature, so I'm sure they can go faster. But I will, guarantee that we are using less precursor. Maybe it's not 28 times less, but it is certainly less. From a film quality perspective, our film at 275, the density is above 2.3 gram per centimeter cubed. You can do densification of films with plasma enhanced ALD, but getting a density for silica above that is challenging unless you do a post-deposition anneal. So again, that speaks to the quality of the film. The refractive index is 1.44, and the dielectric constant, again, measured on silicon is usually around 4, which is pretty typical. But again, I think these last column is really where our film stands out. And as I showed on that previous slide, the breakdown voltage is quite high. We've measured it above 12 on silicon features, like metal insulator, metal capacitor type features. And the leakage, they're pretty comparable. That's one of the places where plasma enhanced ALD really shines. Okay, so the last application that's already out there for GaN specifically, this is that surface passivation. Now, as I was learning about this, there's some really interesting stuff that happens at the GaN interface. So on the left here, I'm showing this schematic of what the crystalline sort of bulk material looks like. And then you have these quote unquote surface states that they just call dangling bonds. This review does a phenomenal job actually talking about what they mean when they say dangling bonds. And so I'll talk about two of them just briefly. One is a gallium vacancy. So you're missing gallium. There's some implications of what that looks like from a nitrogen perspective, but you have a hole where that is. Another one that's quite common is a nitrogen double bond. And so you kind of terminate here and you make a double bond that crosses there. Um, and those have different implications, which I'll talk about in a second. And so, what people found is that with ALD, in this case, trimethyl aluminum and water, remember our TMA from before, here it is again, that works really well for some of those dangling bonds, specifically those nitrogen double bonds, right? Which makes sense. You have something that wants that reactivity and it sort of breaks that bond without disrupting the lattice. But it doesn't do anything for that gallium vacancy that's shown here. So this is what the surface looks roughly like with just a TMA water cycle on the surface. And it did improve things, right? The performance of the devices definitely got better. But what they found is if they did a light anneal, say, 400 C, that they were able to improve things more. There was some, we'll say, mobility of those gallium atoms to fill in those voids. So you just get a much more regular lattice at that interface, right? So again, this is the application that exists today. Again, this is for the GaN hemp device. That passivation layer is shown in blue. So there's, maybe an algan layer there on top. It kind of depends on what you're making. But the idea here for me is that TMA water is great. It's a very common ALD process. It's the most common ALD process, but it might not be the right solution for gallium nitride, right? You might want a nitride interface. This gallium oxygen interface that's now created might be suboptimal. Okay, so this is an area that we think has a lot of potential for ALD in the future, kind of building on that acceptance of ALD in the field already. All right, let's spend maybe the last 10 minutes or so talking about ultra wide bandgap applications. So this is a slide I showed earlier. In the interest of time, I'm not going to go over it again, but again, let's just briefly mention that the point here is you have these higher breakdown fields at a given on resistance. But it's really hard to achieve those, practically speaking, when you're building a device. So, this is where, we really feel like ALD can make an impact. And we wanted to start with beta gallium oxide. It seems from our reading of the literature that this is a place that Mother Nature's kind of playing nice with us, right? There's not too many problems between the ALD and the gallium oxide. Gallium oxide is also very interesting for other reasons. Personally, I think it's super interesting that you can grow substrates from a melt, just like you can with silicon. So from a substrate size perspective, there's a clear path, at least from that perspective, for scaling. It's also relatively easy to dope. These are the structures that we worked on. We worked with Ohio State on this, and this was the doping that they used. It's also fully oxidized gallium oxide. So if you think about putting it in a harsh environment where it's high temperature and some oxidizer around, it's not gonna oxidize further. That just doesn't happen. But the big challenges are you can't make a P-type device, so CMOS is kind of out the window, at least in a traditional sense. And there are some struggles with thermal conductivity. So the goal was, can we achieve avalanche with an ALD dielectric in a metal insulator metal type, capacitor structure? And so we started out with a few ALD films, hafnium oxide and aluminum oxide. If we look at the hafnium oxide here, I'm showing the breakdown, just the raw breakdown here, not normalized for thickness. I'll show that on the next slide. But it looks pretty reasonable. Leakage looks okay. It was a little bit higher than we expected. We estimated the dielectric constant to be around 20. Now, again, all of these metrics are different than we observed on silicon, which is always kind of fun. However, when we went to aluminum oxide, things were quite inconsistent. So, here, pretty much all the hafnium oxide runs overlapped quite well. But with aluminum oxide, we looked at the group looked at a lot of different runs that had some quite a bit of variability. So even if you look at the sort of best case scenario, it still doesn't look all that great. I'll note that these are on different scales here. This goes to 120. This only goes to 30. So these were films of the same thickness. It did have slightly better leakage, but still inconsistent, right? So kind of hard to say that with consistency. So we also estimated the dielectric constant to be around 7.6, which is more in line with what we would expect. Typically, we measure 8 or 9, so a little low, but not too bad. So, one of the things that we learned here is when we did CV sweeps is that they all had some pretty significant hysteresis, which was a bit unexpected. So we kind of deduced that it was some interface defect density sites. Now, just for context, we send these things from, Ohio to Colorado. So there's a lot that can happen in shipping. So we decided that it made the most sense to do a buffered oxide etch to sort of clean off the surface before we put the ALD down. So when we did a second round of tests with just hafnium dioxide, that's what we did first. So if we start on the left here, now we did a thickness series of 80, 90, and 100 nanometers. You'll notice that our leakage current is much lower, about 2 orders of magnitude lower. So again, that interface is critical, right? We also see that, roughly speaking, the breakdown gets higher with higher thickness. But when we normalize for thickness and look at that breakdown field, the megavolt per centimeter, the best performing was actually 80 nanometers. Not exactly sure why, but it's very interesting. This is quite impressive. We're getting close to that theoretical limit of what gallium oxide can do. So I think there's a lot of potential here in using hafnium dioxide as a dielectric. We also know that when it comes to leakage, that if we put a little bit of aluminum oxide in there, we can decrease our leakage even further. So I think there's a lot of potential here for not just ALD, but also the unique stuff that ALD can do, which is those nanolaminates. All right, so I'll put a little bit of information about our hafnium dioxide film here. This is a bit of, we haven't fully released this one to production, so our wafers per hour currently is pretty slow, but we know how to increase that pretty easily. I've already talked about the laminate possibilities. I think there's also a very rich, we'll say, exploration space in hafnium silicon oxide films. I think, from a breakdown and leakage perspective, silica has some very interesting possibilities, especially with our unique crisp film. Our density of a film is quite high, 8.3. We've measured it higher we've actually done some crisp for hafnia as well. So we know we can boost that. Dielectric constant, again, these are all on silicon, measured a little bit lower. I think we know how to bump it up above 20. Certainly when we play some games with nanolaminates, we see some improvement. Same with breakdown. We can really reduce increase breakdown with the addition of aluminum oxide. Pardon me. And leakage current, that's something we're always kind of fighting and always aware of. All right, so finally, the last device I'll talk about is on diamond. Diamond's great because you can imagine if you can get a device made, you can get even smaller, right? So, and diamond has good thermal conductivity, so heat's not a problem, but diamond is quite inert, right? So putting films on diamond is a challenge. As I mentioned before, just patterning, making features in diamond is a challenge. There are a lot of people working on this, doing some very interesting stuff. We've done a little bit of work trying to make some Schottky barrier diodes. So here's an example of just a mesa where we coat the mesa and the rest of the plateau here with aluminum oxide. And actually we're able to measure some properties, which was great. That means our ALD film was high quality, that it was well adhered. So even though diamond is inert, it looks like TMA water can do it. Of course, the breakdown voltage was lower than expected. I think here is where we have to think about again, what those interface defect sites actually look like, especially after etch, and what we can do to kind of clean that up. So, again, the sort of parameters of the device, resistance and ideality factor, it seemed reasonable, but it wasn't anything that was sort of mind-blowing yet. But, I was still really proud that we were able to get functional diodes. All right, I have about 2 minutes left, so without repeating myself too much, ALD is a wonderful technique, very high quality film, very elegant, but it's slow. The good thing is we have a reactor that helps speed things up. Both in the R&D space, we do more experiments, as well as in the manufacturing space, process more wafers per hour. We've applied our technology to wide band gap applications of silicon carbide and gallium nitride. Again, the three key ones are moisture barrier, dielectric film, and passivation. And we've started to explore some ultra wide band gap materials, gallium oxide and diamond. And so with that, I'd really like to thank you all for your attention. This was a lot of fun for me. I had a really good time preparing these slides and just thinking about the problems that I talked about. If anybody wants, feel free to take a screenshot. This is a QR code. It will send me an email if you have any questions. I'm always available over email. So with that, again, I'll thank you all again. Thank Power America for putting this on and open the floor for questions.
Okay, fantastic. Matt, thanks so much. Really appreciate this conversation. I've learned a lot about Forge Nano. I've learned more about ALD and about some of these emerging applications for the technology as well. I'd definitely say that I would agree with one of your comments. I feel like I thought that I knew some things about ALD, and I've definitely learned and gotten some clarifications through this presentation. So really grateful for that. If folks do have questions, please feel free to submit them in the Q&A module. So again, at the bottom of the screen, you can click on the Q&A button, type questions in there. In the meantime, Matt, I do have a question for you as well. You've mentioned a number of different benefits. So you kind of gave us the disclaimer up front, not disclaimer, but Forge Nano is in the business of selling equipment, right? And you've mentioned a number of different benefits from being able to achieve devices with similar functionality, but different levels of thickness as well as reduced precursors. So how do you communicate about cost of ownership, right? Like
Mm.
how do these things translate into actual sort of investments into
Yeah.
technology platforms?
That's a great question, Manuel. It's something we talk about a lot. Before I answer that question, though, I'm glad that at least one person learned something. So I feel like I've done my job. So thanks for telling me that. I feel like it was worth my time. All you need is one. So yeah, translating these benefits of faster speed, single wafer tool, less precursor consumption also means less energy consumed, right? So if you think about wafers per hour, you can achieve much higher wafers per hour while consuming less energy and less precursor. One of the things I didn't touch on because of time is that draw control also helps to protect part of the chamber. So our preventative maintenance schedule is, we can extend that because we're sort of protecting the coldest part in our chamber, which is the walls, which is where you typically get the most impact from ALD. So, from a cost of ownership perspective, it's a little hard to quantify, but all the feedback we've gotten from customers is, we don't have to change precursors nearly as often, which takes time, right? So that's not just a cost of precursor, it's also a time saver. We don't need to change certain parts of our tool or service them as often, which again saves time. It's not just the cost of those parts, it's also taking the tool down for a day or two. And we're still able to do it at speeds that are comparable to batch reactors, which is, again, I think the standard for this, 200 millimeter and below market. The sort of adage that I like to tell people is, we're trying to give them 300 millimeter tool quality, but that's tailor made for 200 millimeter at that 200 millimeter price point. So that includes, that cost of ownership.
Fantastic. Definitely appreciate that. That makes a lot of sense. I'm curious about sort of your process for working with partners. So it sounds to me like you all would essentially have to do a lot of internal, I guess one maybe R&D, but there's a lot of internal work that you all have the capability to do and that you do internally in order to help to, work with device manufacturers, right? So can you talk about that relationship? I'm sure there are some folks here in the Power America community that maybe aren't working with you yet. So what does that relationship look like in that collaboration?
Yeah, that's a great question. There's a lot of different ways that we can collaborate with people. I do would like to stress that, again, as I said at the outset, we're ALD experts. So we don't always have that device fabrication expertise, and we certainly don't have enough tools to make our own devices. So whenever we need to characterize, say, like a dielectric property of a film, we have to have help. We need collaboration, or we pay somebody to do it. So, there's a range of ways that we can engage. I would say the most typical is what we would call a customer demo, where somebody says, "Hey, I need to buy an ALD tool. I want to try your film on my stuff." We do a couple of calls and talk about the goal of the engagement. We'll write a statement of work that outlines all the experiments and all the wafers and what the goal of the engagement is, and then we run the wafers and assess. So that's sort of the most typical way. We also do like joint development type projects where it's a little bit less defined for either like a tool sale or even if an application is right for ALD, if ALD is the correct solution. So, I think that passivation layer, moving away from alumina, like that's a good example of an engagement where we would be working with somebody to develop something novel that they hope would be able to be integrated, and then, turn into a product. So that's more of a proof of concept or joint development type project, which we do quite often, and we have separate agreements for that. And then I think the third one, we do a lot of grant work still. So, we engage with people in the Power America community and in other places to, write and submit grant applications to solve very specific problems. Sometimes we are the prime investigator, but I would say a majority of the time we're a subcontractor that gets pulled in. It's rare that most grant calls are ALD specific enough for us to be the prime, but we do have a couple that we are in charge of. So I would say those are the three main mechanisms, and I'm sort of happy to discuss any of those in specific if people have questions.
Awesome. Definitely appreciate it. Let's see. It does look like there is a question here just about the metrology challenges related to the work that you're doing. Great question, by the way.
Let's see. I don't see the question. Let me see if I can get it pulled up here.
Okay. Yeah, so I would just ask in general, in the work that you're doing, especially as it relates to wide band gaps and applying ALD, are there challenges related to metrology or measurement science that you encounter? And I guess what do those look like and what kind of innovations are you considering?
Yeah, we absolutely are. I think, as I mentioned a few times through the discussion, a lot of things matter, right? So what material you're building your structure out of, what that interface looks like. We have sort of learned a lot about that process. So, how those different structures and how those interfaces interact with metrology is, I think, critical. So, we've learned that there's certain frequency ranges for us to measure in that are more reproducible than others. But sometimes going outside of the common like frequency range for, let's say, a CV sweep can tell us a little bit more about what's going on. So, we've also seen that like contact techniques where we're actually building like a MIMCAP structure versus non-contact techniques can give us wildly different results. So, sometimes one negative metrology result can be, we'll say, spurious, right? Because there's something in that technique that is that's not being accounted for. So my approach is always, let's measure these things on as many devices in as many different ways as we can to make sure that we're sort of randomizing our experiments in an intentional way. So, we've worked a little bit with NIST to and other national labs to kind of look into this and try and understand our films a little bit better.
Fantastic. Right, I was gonna ask if NIST had supported some of the work, so happy to hear that. I just work
Yeah.
very closely with their measurement sciences division. So there's another question in about so the question is, what do you project for future in situ opportunities, and specifically related to chamber and loading and handler equipment?
Yeah, I think that's a great question, especially for this field. GaN and silicon carbide, they really seem to like some sort of surface pretreatment. What exactly that surface pretreatment looks like, I think is we have a good idea, especially for gallium nitride, but silicon carbide seems to be a little undefined. But I would say having like a plasma pre-chamber that's a very light plasma, some type of ICP without too much ion bombardment. I think that could really do a lot to prepare a lot of surfaces. I mentioned we've sort of relied on buffer oxide etch. I don't think that's what you want to do in a manufacturing state. So I think there are other ways that you can mimic something like that, whether it's a vapor phase HF or a plasma pretreat, that can get you at the same or perhaps even a better outcome. I also think, again, as an ALD person, I have to admit that atomic layer etch, our sort of complementary technique, has a lot of value in this space as well, where you can imagine having, that image I showed earlier of that bulk GaN and the interface states being different. If you can just remove that with an atomic layer etch and go back to that bulk interface, I think there's a lot of power there. So I do think there's also a place for a complementary atomic layer etch module to sort of prepare that surface, whether it's in tandem with that plasma or in replacement of that plasma clean chamber. I think that's yet to be determined, but I think there's a lot of really interesting space there.
That is interesting. Appreciate that. All right, down to the last minute. I'm curious. We talked about working sort of with companies. I'm also curious to know if you all work with folks in the research space, whether that's national labs, universities that are conducting research in ALD and looking to push innovations
Mhm.
towards commercialization.
Yeah, absolutely. One of the roles we play quite often is like a manufacturing transitional partner for a lot of universities and national labs. So, we'll typically go after some sort of grant or government funding to help us, fund that transition of that technology. So, there's a bunch of agreements that we have in place where we, make sure everybody's IP is protected and all that kind of fun stuff. And then we can explore the best route to transitioning that proprietary technology. But yeah, I mean, I think that's one of my favorite areas. How we take something from the lab and turn it into a product. I think I've done that a few times in my career, and it's very rewarding. So that's a great question, Emmanuel, and I think that's something that I'm personally very interested in.
Awesome. I'll give a selfish plug then beyond government programs. Also, to the folks listening, keep in mind Power America's funding call. This sounds like a great opportunity to work with a great partner. If you are a device company looking at innovations or you're a researcher looking at technology translation, Power America's future funding call to be released in the fall could be a great way to de-risk some experimentation around efforts like this. And our summer workshop coming up in August would be a great time to get together and talk about those concepts in preparation for submitting a concept paper to our fall funding call.
Absolutely. Hey, we'll be there. So if anybody wants to have a conversation and wants to do it in person, me or my boss will be there. Maybe both of us. We'll see.
Okay,
Absolutely. That's a great
fantastic.
call. Great, great, great plug. Thank you.
Awesome.
Great plug. I love
I
it.
appreciate it. Well, Matt, thank you so much. This has been an amazing presentation. Thanks for everybody who attended as well. I hope you all benefited from it, and we'll look forward to having you all next time in our next seminar. So, Matt, thanks again.
Yeah, thank you. Appreciate it. Appreciate it. Enjoy.
Absolutely. Take care, everyone. See you
Take
next time.
care.